All right, as promised, we are going to do some practice genetics problems. By we, I mean me, and you will follow along. And hopefully, after doing a few of these Punnett squares, you will have a better understanding of how to do this. All right, the first question in this oompas worksheet says, oompas generally have blue faces, which is caused by a dominant gene. The recessive condition results in an orange face. Sorry, I blurred that out. Okay, so the recessive condition results in an orange face. First thing we do when we are doing genetics problems is we write down our key, our allelic key, to show the genotypes and phenotypes possible for Oompa Loompas. Okay, so let's use the letter B since B is encoding for blue. Okay, it's the dominant trait. So B, capital B, you need one copy and you would get a blue face. Okay, in order to get an orange face, and there's another way that you could get a blue face. This is a heterozygote or heterozygous genotype. How else could you get a blue face? Well, you could have a homozygous dominant. In order to get an orange face, what do you need? 2 copies of the recessive allele will give you an orange-faced Oompa. All right, so that's what you should do every time you are doing the genetics problem. Figure out what your dominant allele is, what your genotype is to get a particular phenotype. All right, second one. 2 heterozygous Oompas are crossed. What proportion of offspring will have orange faces? 2 heterozygous Oompas. What does heterozygous mean? It means this. This is a heterozygote. Okay, 1 copy of each allele. So if I was going to cross 2 heterozygotes, I would draw my Punnett square. Thanks, OneNote. Okay, I'm going to have possible alleles from mom and possible alleles from dad on the other side. And then I'm going to cross them. And this is what I get. I get a homozygote, I get a heterozygote, I get a heterozygote, and I get a homozygote. Okay, good practice is to always write your dominant allele first. And if you're writing the dominant allele first, you know that in this part of your Punnett square, you're always going to have your homozygous recessive allele. Okay, so what proportion of the offspring will have orange faces? Yeah, you need 2 copies of the recessive allele to get an orange face. That would be 1 out of 4 or 25%. That should be more clear now. I'm going to make my eraser, stroke eraser, cool. Let's do the next question. All right. Next question says, a blue-faced Oompa is married to an orange-faced Oompa. They have 8 children. How many will have blue faces? I don't know. This is just probability, right? We can't really guess how many would have orange or blue faces out of 8 children. We just know by doing the Punnett squares that every time a sperm and egg meet, this is the possibility of offspring that we would have. So this is kind of like a trick question. Okay, that part that says they have 8 children, don't let that throw you off. Okay, so blue-faced oompa, homozygous. They are blue-faced and homozygous, right? So that means they're homozygous dominant, is married to an orange-faced oompa. Okay, orange, you can only be homozygous recessive. What do we get? When you do these over and over and over again, you get better at them. All right, how many children will have blue faces? All of them. Okay, all of them will have blue faces because in the combination of alleles that you can have from mom and from dad, there is zero possibility that any of them will have orange faces. Okay, so that was a trick question there. Let us erase and do more Punnett squares. All right, here we go. I am learning how to use a computer. I have a feeling there's another Punnett square here. Okay, number 4, right here. Otis Oompa has an orange face and is married to Ona Oompa, who has a blue face. They have 60 children. 31 of them have orange faces. What are the genotypes of the parents? Okay, I don't know. That's 60 and 31 kids. That's confusing. Okay, where do I begin? I begin with my Punnett square. I begin with the possible allelic combinations that the parents could have. Okay, Otis has an orange face. Otis can only be this, right? Because he has an orange face. He needs 2 copies of the recessive allele. Ona has a blue face. Okay, so blue, she can be heterozygous or homozygous dominant. Now, right off the bat, if I made Ona homozygous, is there any possibility that they could have orange faces? That their kids could have orange faces? No, right? Because look what happens if we cross these two, Otis and Ona. They would have no children with orange faces. All their kids would be heterozygous. Okay, so Ona has to be a heterozygote. Doesn't matter how many kids they have. Okay, so genotypes of the parents here would be Otis has an orange face and Ona has to be heterozygous. I hope things are getting clearer and clearer. Okay. Number 5. Just erase. Number 5. Odie Oompa has a blue face. In fact, everyone in Odie's family has a blue face, and the family boasts that it is a pure line. Much to his family's horror, he married Andi Oompa, who has an orange face. What are the genotypes of their children? Is Odie's line still pure? Okay, this is what is called a true breed. Okay, everyone in Odie's family has a blue face. Okay, they've had blue faces in their families for years. Okay, so if their kids, if he marries Andi, she has an orange face, right? So right off the bat, Andi is homozygous recessive. This question is leading us to think that Odie is homozygous dominant. Okay, genotypes of their children are going to be big B, little b. Okay? We don't know for sure that Odie is homozygous dominant. The pure line and everyone in his family having blue faces should lead us to believe that he's homozygous dominant. All right? And they would have kids, all kids with blue faces. So his family can rest assured. Okay, next question. Ona divorces Otis because his family sucks and marries Otto. Otto has an orange face. What is the probability that Ona and Otto's children will have orange faces? Easy peasy lemon squeezy, this one. Okay, these are like the same problem over and over and over again. Okay, so what we're seeing here is they're telling us that Otto is homozygous recessive. All of their children will have orange faces. I don't even need to do this one. Okay, so here are Otto's genotype and Ona's genotype. There's no way that they could have any children with blue faces. All right, now we are going to draw a line. Okay, and now we are going to get into what is called codominance. Fun, fun, fun. Now we have, okay, I'm going to change my color because I can. Cool, good enough for me. Okay, so here we go. Oompas can have red, blue, or purple hair. Purple hair results from the heterozygous condition. Okay, now that you have an intermediate, okay, purple hair, you get a different color from the heterozygous condition. Now you should realize that we are talking about, oh, that's still a highlighter. We are talking about, hey, okay, there we go. Now we're talking about codominance. Okay, this is the same as, oh, I'm sorry, this is incomplete dominance. Shoot. My bad. I was all excited to talk about codominance. Okay, this is incomplete dominance. Okay, that you have an intermediate condition. Okay, so make a key showing genotypes and phenotypes for hair color. Is this an example of codominance or incomplete dominance? Okay, this is the same example from the book as the white and red flower, that when you cross them, you get a pink flower. Okay, that's incomplete dominance. You get a phenotype that is somewhere in the middle between the two other phenotypes. Okay, so step by step, make a key showing the genotypes and phenotypes. I'm going to do let's go with red. Okay, that is red hair. This is blue hair. And if you get a heterozygote, you get purple hair. Okay, we'll talk about why that is not codominance. Okay, codominance is like blood typing. So this is incomplete dominance. Orville Oompa has purple hair. Okay, Orville Oompa has purple hair. He has, bam, that phenotype. Opal and he's married to Opal Oompa, who brags that she has the bluest hair in the valley. Okay, how many of Opal's children will be able to brag about their blue hair also? Square time. Okay, Opal has the bluest of the blue hair. Okay, so she has that phenotype. Got it? Okay, how many? Yeah, 2 out of 4, or 1/2. That's a 2. Okay. All right. Next question. Eraser. Lonely. I'm Mr. Lonely. I'll miss you guys. All right. Next question. One of Opal's children is born with shocking red hair. Is Orville the father of this child? Show the square to prove your answer. But wait, Opal swears she's been faithful and claims that the hospital goofed and her baby got mixed with another. Is this a plausible explanation? Show the square to prove your answer. Drama. Okay, I want to fix this line. This is a really ugly line. Okay. Oh dear. I have no chance as an artiste. Okay, so who are we working with? We got Opal. Opal has the bluest blue of the blue hair. Okay, so she's RR. Orville has purple hair, so he can only be this. I shouldn't have even erased that. Okay. One of her kids has red hair. Is that possible? No, it's not possible, right? Because they would have to be homozygous, right? So that's basically the same square as before. I don't know why I erased that. That was silly. Sorry about it. I wanted to make it nicer. Okay. She's been faithful and her baby got mixed up with another. Well, I think that's for Opal and Orville to decide. What we know from doing this square is that it is impossible for any of their kids to have red hair based on their genotype. Okay? Because you have 3 different colors for 3 different phenotypes. All right, so Orville and Opal are going to have to work it out. Next. Oh, we're almost done. Okay. Draw. Pen. Olga Oompa has red hair and marries Oliver Oompa, who has blue hair. Okay, gotta go back to my key. Okay, so purple is, go away. Hide. Purple results from the heterozygous condition, and we said blue is the homozygous little lowercase condition. All right, so go back to, I'm going to write that first so we can be consistent. That's furful. and that is red. Okay, Olga has red hair and Oliver has blue hair. Okay, again, they're just trying to throw you off with how many kids they have. We don't know because every time they have a new kid, you repeat the probability. Okay, so here we go. Olga has red hair. Oliver has blue hair. Their children are all going to be heterozygotes. Okay, their kids are all going to have purple hair. I don't care if they have 5,000 children. They all have purple hair. Okay, because you're crossing a homozygote with a homozygote, you get all heterozygotes. This is incomplete dominance. So when you have the heterozygous condition, you get purple hair. Eraser. Let's see, who do we have next? Who's making babies? Okay, Olivia is married to Otto, and they both have purple hair. Easy peasy. They're both heterozygotes. What color hair and in what proportion would you expect their children to have? Heterozygotes are fun because you never know what you're gonna get. Okay, well, you do actually know what you're gonna get. You have 1 out of 4 with red hair, right here. 2 out of 4, gosh darn, okay, 2 out of 4, or 1/2, with purple. Bear with me, y'all. And 1 out of 4 will have blue hair. Terrible. Okay, so that is the proportion of colors of hair that their children would have. What if we ask you what proportion of their children are homozygous, right? If I change the question and I ask you about the genotype as opposed to the phenotype, then you should be able to tell me that half of them are homozygotes and half of them are heterozygous. Okay, so keep track of your vocab here. Are we talking genotype or phenotype? Cool. Last one. In the land of Oompa, blue hair is highly valued. Blue-haired Oompas even get special benefits. What? That's garbage. Okay, Oscar Oompa has purple hair, but he wants to find a wife that will give him blue-haired children. What color hair should his wife have? What would be his second choice? Okay, we're going to play matchmaker real quick. So, Oscar has purple hair. Oscar is heterozygous. Okay, he wants to have blue-haired kids. Okay, in order to have blue-haired kids, they need to have 2 copies of this allele, right? So you need to have either, he needs to find a wife with blue hair, right? Duh. So then he would have half of his children with blue hair. Okay, second choice. Second choice should be what? What should his second choice for wifey be? Yeah, purple, right? Two heterozygotes. Bottom right corner of your Punnett square is going to give you a homozygous recessive. All right. Oh boy, I drew an extra R in there. Yeah, he can have a wife with purple hair and still get blue-haired children. I hope that helps. I'm just going to finish this for... Okay, I hope that helps. And if you have questions on this worksheet, holler.